This is your presenter, Asloob Mudassar, and I am presenting slide number 15D of the course on atomic and molecular physics. In the today's lecture, I shall be covering the Grotrian diagram of the atomic nitrogen and the JJ coupling. This lecture is in continuation of the previous lectures, and this is the fourth lecture of the series of many electron atoms. And in the last lecture, I discontinued my lecture because I found a discrepancy in the arrangement of energy-wise distribution of the terms related with the second excited states of the atomic nitrogen. So I shall continue from the same point. That is, I was discussing terms in second excited state of the nitrogen, and the second excited state was 2p2 and 3p. And first of all, you know that 2p2 electrons will be dealt first with their angular momentum L1. L1 is equal to 1, L2 is equal to 1, and their total quantum number capital L will be constructed as 210 with the term symbols as D, P, and S respectively. Similarly, their spin angular momenta will be combined as mod of S1 plus minus S2 with parallel spins will be equal to half, multiplicity will be 3, and when they are in anti-parallel orientation, then half minus half will be equal to 0, and their multiplicity will be equal to 1. And you know that when we discussed these terms, you see that we have the terms D, P, and S, and now I can use the multiplicities with them. So after obtaining the multiplicity of these points, I have written these notations as 3P, 1S, and 1D. So these are the terms that I have obtained through the electrons in the inner core, which belongs to 2p2. Now I am going to combine these terms with the contribution from the 3p electron. That is, these terms 3p, 1s, and 1d, which are obtained from the core 2p2 electrons, will now be combined with the 3p electron. So the combination is simple and is given by the formula, that is the resulting quantum number L of the system will be equal to Lc plus minus L, and the resulting spin quantum number of the system will be equal to Sc plus minus S, where Lc will be obtained from 3p, and then from 1s, and then from 1d, because this is the core angular momentum quantum number, and these are the core terms. These are the terms related with the core electrons, that is the 2p2 electrons. These will be referred to as the core terms, and their angular momentum will be referred to as Lc, that is the core angular momentum quantum number, and similarly Sc as the core spin quantum number. Now you see that you can see the quantity L and S, and these are the angular momentum quantum number, and the spin quantum number of the 3p electron, which is L is equal to 1 and S is equal to half. So after combining these one, I have obtained for the 3p core electrons, when these are combined with the 3p electron, I obtained the following terms. So these were the terms that I have obtained when the 3p term, so let me show you that one. When these 3p term from the core contribution was combined with the 3p electron, then these terms were obtained. You see that these are two types of terms: doublet terms, quartet terms in S symbol, similarly doublet and quartet terms in P symbol, similarly doublet term and quartet term in D term symbols. And you see that I have also written the total quantum number J of the atoms also with each term. And I have also explained that how these will be obtained. So let me just for a quick demonstration, I am going to explain. For example, for this, let me explain for example for this 4D1. 4D not this 0, this O at the top as a superscript stands that these terms have odd multiplicity. So the multiplicity of these terms are odd. That's why I have written them as O as a superscript with each of these terms. So let me explain the values of the quantum numbers over here. So the total quantum numbers of the atoms of corresponding to this D term. You know that for the D term, we have the value of the orbital quantum number equal to 2. So L is equal to 2 over here. And when the multiplicity is 4, then it means that we have the spin quantum number, capital S is equal to 3 by 2. So if you combine the D, the value of D, which is 2, so 2 plus minus 3 by 2 mod, then it will give you 1 half, 3 half, 5 half, and 7 half. Similarly, I have written and I have arranged these quantum numbers in energy wise. That is, the half has the lowest quantum has the lowest energy, then 3 by 2 is the next higher in energy, then 5 by 2, and then 7 by 2. So these terms were obtained from the 3p core terms, which when combined with the 3p electron, then you see that I have also demonstrated that when 1D core term, this is the core term, 1D is the core term, when this core term will be combined with the 3p electron, then of course then these three terms will be obtained. So 2p, 2D and 2F terms will be obtained. Similarly, when the term 1s, which is the core term, will be combined with the 3p electron, then of course this term will be obtained, which is the 2p. 1 half and 3 half terms will be obtained. Now you see that now I have obtained these terms, which is shown over here, then shown for the 1D, these terms, and then for the 1s we have the terms. Now I have to arrange all these terms in the energy distributions, energy wise distributions. So first of all, I shall arrange them in the distribution of this 3p electron, this 3p term, because you see that the core terms were 3p terms, 1s terms, and 1p terms. So for the, since the multiplicity is the highest for these 3p terms, so first of all I shall arrange these 3p all the terms which were obtained using the 3p terms with the core with the 3p electron. So this 3p will get the preference, since the highest this is the highest multiplicity term, so it will have the lowest energy. So all the terms corresponding to 3p will be arranged first, and then I have 1s and 1d. You know that here the multiplicities are the same, both 1s and 1d have the same multiplicities, but you know that the value of orbital quantum number is higher for the d term, so d term will be lower in energy in comparison with the 1s terms. So also second, first of all I shall rearrange all the terms energy wise corresponding to 3p, then I shall arrange all the terms corresponding to 1d term, then I shall arrange all the terms obtained corresponding to 1s terms. So these will be arranged energy wise according to this pattern. First of all 3p terms, then 1d terms, then 1s terms. So you see that these are the terms corresponding to 3p terms. When this 3p of the core terms combined with the 3p electron, then of course these terms were obtained, and now I have to arrange these terms first in energy distribution. That is lowest under the terms with the lowest energy will be on the left hand side, and the term with the higher energy will be on the right hand side. So you see that in the previous lecture, I didn't find this term, which was the 4D term, was not available over here in the energy distribution. So I discontinued my lecture over there. Now I am putting this term over here. This is the term with the maximum multiplicity 4 term is over here. And I have written. And you know that there is another term which also has the 4 multiplicity. But you know that since the value of D is higher, if the multiplicities are the same, that is 4D has the same multiplicity as the 4p terms, but the value of the orbital quantum number is greater for the t terms, so it will be lower in energy. So this 4t term will be lower in energy in comparison with the 4p terms, and these total quantum number j of the atoms have been arranged. The lower one has lower energy, and the higher one, for example 7 by 2, has highest energy for these 4t terms. Similarly, the next term is the 4p terms, and the next to that one is the 4s terms. because these three terms, which is the 4D term, 4P term, and 4S term, out of these three terms, the term D term will be arranged in the lowest order of energy, because this has the highest value of a quantum number, which is capital L is equal to 2, and then the term with capital L is equal to 1, and then the term with capital L is equal to 0 will be arranged. So you see that similarly we have the terms with the doublet or with the multiplicity equal to 2, and then of course the maximum value of D has L is equal to 2, it will be arranged then the lower value of L, which is L is equal to 1 for the P term, and then the lowest value of L will be arranged in energy wise. So you see that these terms have been arranged from left to right. The left terms have the lowest energy, whereas the term on the right has the highest energy. And these terms, that is 1, 2, 3, 4, 5, 6, these 6 terms are the terms which were obtained from the from this 3p electron. So let me show. Okay, from this 3p term, which is the core term due to the 2p contribution of the electrons. So all the terms I have arranged corresponding to the 3p terms have been arranged over here. For example, in this, now I have to arrange the terms that I have obtained corresponding to the 1D term, and these are listed over here. So similarly, you see that you can see that all these terms have the multiplicity equal to 2. That is, these are the doublet terms. So since the multiplicity is the same, so I cannot arrange them energy wise due to the multiplicity. So the next parameter that I shall take to arrange them is the value of the orbital quantum number L. So F term has the highest quantum number L, which is equal to 3. Then the term D, which has a value of L is equal to 2. Then the P term, which has value of orbital quantum number L is equal to 1. So I shall arrange them like that one. So the first I have arranged the F term, then the D term, and then the P term. Because these terms are the doublet terms, so the value of L is the greatest for F term, then for the D term, then for the P term, and then for the S term, one S term, I am left only with this 2p term, which is the doublet term. So this will be followed at the end. So I have this term lying at the end of this one, which is 2p 1/2 and 3/2. And you know that all these terms which were related with the 2p2 and 3p electrons, which was the second excited states of the nitrogen atom, these terms have been arranged energy wise. So these first three terms belong to the 1D term, and this term belongs to 1S term. And of course, these many terms belongs to 3P term. Now you see that I have studied and I have presented the term symbols corresponding to the ground states of the atomic nitrogen. Then corresponding to the first excited state of the nitrogen, which was 2p2 and 3s, and then the next higher state for the p state was 3p2 and 3p. So I have obtained for these two distinct higher energy states, which were 2p2 and 3s, and the next higher energy state was is 2p2 and 3p, and the ground state was 2p3. So corresponding to this one, I have obtained all the energy terms. Then I can arrange these terms in the energy or in the Grotrian diagram. You see that I have modified the Grotrian diagram over here a little bit in comparison with the conventional terms, because number of terms are much greater. So I can arrange these terms in terms of the doublet terms. For example, I have arranged the doublet terms first in the first column, and then the quartet terms with the multiplicity 4 have been arranged in the second column. And you know that the transitions only takes between the doublet terms, and the transitions will also takes place only within the terms within the quartet terms having the multiplicity 4. However, there will be weak transitions from the quartet to the doublet terms. These weak transitions have been shown over here. That is, we are going from the quartet terms to the doublet terms, but these are the weak terms. Weak terms and the stronger terms are those which are shown in each individual columns. For example, I have distributed them in terms of the total orbital quantum number L of the atom. For example, 2s term in the first column, then 2p terms in the second column, 2d terms in the third column, 2f terms in the fourth column. So these terms have been arranged with respect to the doublet terms in energy wise distribution. For example, here 2s has the highest energy, then 2p has then lower energy, then 2d further lower energy, and 2p has the lowest energy among these two doublet terms. Then of course the quartet terms, this 4s term has the highest energy, then 4p terms, and then 4d terms, and then the 4f terms. I have not shown those terms because of the space. If otherwise I have to narrow down this figure and the things will not be clear. So you see that the next two column of this quartet will contain 4d and 4f terms, which I have not shown. And you see that within each column I have shown some transitions, and these are the strong transitions. For example, these strong transitions in the first column have been shown. Then from the second column, strong transitions have been shown. And then in the third column, I have shown the transitions from this to the ground states. And then the transitions I have shown for this 2f states, some transitions from the quartet to the 2f and to the 2d transitions have also been shown, but these are the weak transitions. Because you know that we have delta S is equal to 0 shown over here. And this delta S means that the multiplicities must be the same. That is, the transition between the doublet terms will be the strongest terms, and similarly the transitions between the quartet terms will be the strongest terms, because they satisfy delta S is equal to 0. That is, must have the same multiplicity for the transitions to occur. But if I have shown some transitions which are violating the delta S is equal to 0, but these are the weak transitions. And the strong transitions are shown. For example, in each individual columns, these are one of the strongest transitions. And then you see that these obey the transitions from the odd parity to the even parity and vice versa. So the stronger transitions will be from the odd to even, or from the even to odd transitions will be the strongest transitions. The other selection rules that will be followed by these transitions will be delta S is equal to 0, delta L is equal to 0 plus minus 1, delta J is equal to 0 plus minus 1. These are the strongest transitions. And you see that I have shown some arrows over here to indicate that these are the allowed transitions. These can be used in the emission pattern, and some parity change transitions have also been shown. But you know that there are some transitions which may be violating delta S is equal to 0, but they are obeying the other transitions. These transitions may be referred to as the weak transitions. So you see that you can expand this table and you can easily see and convince yourself that these transitions obey these rules which I have listed over here. And remember that for the quartet, there are two more columns. The other columns will contain 4d terms and 4f terms. And you know that in this column, if you go energy wise, that is the first column contains the terms with the highest energy, then the 2p terms, then the 2d terms, and then the 2f terms among the doublets terms. And if you follow the quartet terms, the similar pattern is given. 4s term has the highest energy, and then the 4p terms, and then the 4d terms, and then the 4f terms. So these have been energy with the energy, strongest energy in the first column, then in the second column, then in the third column, and so on. Some important spectral transitions have been listed over here, and their wavelengths have been specified in angstrom, and their intensities have also been compared. For example, this one has the in arbitrary units. This is the intensity in arbitrary units, and you see that 1, 2, 3, and 4 are these are the minimum values of intensities. And then you see that there are some transitions which have drastically high values of intensities. And I have shown their lower energy terms and their upper energy terms in which the transitions can take place. And I have also shown the multiplet numbers there. Referring to the Grotrian diagram given in the previous slide, these odd energy terms, these odd energy states, and you know that what are the odd energy states? 2p2 and 3p states. The terms that we have obtained for the 2p2 and 3p states were the odd energy terms. For example, over here you can see that the 2p2 and 3p terms, all these terms are the odd energy terms. And of course, these odd energy terms corresponding to the second excited state will lie higher in energy in comparison to the first excited state, which is 2p2 and 3s. And 2p2 and 3s energy states are the even energy states, which I have mentioned in the previous lecture. And these energy terms corresponding to 2p2 and 3p are the odd energy terms, and lying higher in energy than the terms corresponding to 2p2 and 3s electron, which were the even energy terms. So the transition from the odd energy terms to the even energy terms will take place. Referring to the Grotrian diagram, these odd energy states are found in the top region of their respective L columns, because these odd energy terms corresponding to the 2p2 and 3p distribution of electrons. Their transitions will occur to their lower energy states of even parity, and you know that 2p2 and 3s is the even parity terms that we have discussed. I have not discussed 2p2 and 4s, 4s electronic distribution and their corresponding terms, but their corresponding terms can similarly be the same as the energy terms obtained for the 2p2 and 3s electron, and both of these one will contain even parity terms. So the transition from the odd parity term and the even parity terms will take place, and the even parity term which are due to 2p2 and 3s electron, they will be lying lower in energy in comparison with the odd energy terms, because odd energy terms correspond to the second excited state of the electronic contribution, which is the 2p2 and 3p electronic contribution. And all these terms due to 2p2 and 3p are the odd parity terms. So the transition from the odd parity to the even parity terms will take place. And you know that the ground term is also the odd parity term. So the transition from the odd parity to the odd parity term will not take place. However, the transition from the first excited state, which is 2p2 and 3s, which is the even parity term, the transition from this to the ground state will take place. So their transition to the ground state, which is 2p3, being an odd parity, is forbidden by the Laporte rule. So from the odd to the odd is forbidden due to the Laporte rule. But from the even to the 2p3, which has the odd parity term, is allowed by the Laporte rule. So you see that this is what I have completed my discussion on the atomic nitrogen, on the first excited states of the atomic nitrogen, which was the 2p2 and the 3s electronic configuration. And then I have also discussed the electronic configuration 2p2 and 3p and their relevant energy terms. I have also distributed those terms energy wise, and I have also given their distribution in the spectrum over here. And then I have shown some energy terms, not all, but some of them. And some of them have also been specified over there, which and their wavelengths are given, their intensity distributions are given, their lower and upper states are given also. So you can consult by magnifying this diagram, and you can see that which of the transitions are allowed and which are weak, which are stronger. Now the next one I am going to discuss the JJ coupling. This is a new type of coupling, and this is the first time I am going to discuss. I have discussed LS coupling many times in one of the previous lectures, but in the today's lectures, that is in the previous 3 lectures, I have completed my discussion on the LS coupling in much greater detail. Now I am going to discuss JJ coupling briefly. JJ coupling occurs only for heavy atoms, because in heavy atoms the type of interaction is changed. For example, in the heavy atoms, for an individual electron, the value of the orbital angular momenta and the spin angular momenta, the coupling between these two quantities for a single electron becomes much stronger as compared with their coupling with the other electrons. So for the individual electrons, the LS coupling, that is the coupling of the orbital angular momentum and the spin angular momentum, becomes much stronger. And due to that one, the JJ coupling arises. That is the spin orbit coupling of these individual electrons becomes much stronger. And this strength and this coupling becomes greater and greater as we go with the higher values of the nuclear charge Z. That is, for heavy atoms, the interaction between L and S of the individual electrons becomes much greater than in comparison with the L contribution with the other electrons and the coupling of S with the other electrons, as in case of LS coupling. Now you see that here I am talking about LS coupling in this paragraph. Spin orbit coupling, that is Li and Si, that is the ith parameter of orbital angular momentum and the spin angular momentum of the ith electron. The interactions for a single electron is larger compared to these. That is, Li and Lj of two different electrons of the ith and the j electron is much stronger. So Li will couple with Lj. Similarly, Si will couple with Sj. This will form total value of capital L. This will form total value of capital S. That is why this is called LS coupling. So this as LS coupling will occur when the orbital angular momenta of different electrons are combined and the spin angular momenta of different electrons are combined. So different values, so we constitute total capital value of capital S and the total value of capital S are constructed. So total capital L value and total capital S are constructed in the LS coupling, and then they are combined to construct the capital value of J, that is the total angular momentum are combined. So let me show you the diagram below so that the things becomes more clear. This is the diagram corresponding to the LS coupling. So you see that this red dot corresponds to one electron, and this sky blue dots correspond to the second electron. So L1 will combine L2. You know that these are two different electrons. L1 is the orbital quantum number of the first electron. L2 is the orbital quantum number of the second electron. In principle, the quantum numbers are not combined. In principle, their angular momenta or their magnetic moments are combined. But you see that here I have given this diagram not in terms of their magnetic moment or in terms of their angular momenta, but I have given this diagram in terms of their quantum numbers. But more precise diagrams will be given in terms of their magnetic moments. So here I have shown only the quantum numbers. So the quantum number of the electron 1 and the quantum number, orbital quantum number of the electron 2 will combine together to give you the total quantum number L of the electron or the atom. Similarly, the spin quantum number S1 of the first electron will combine with the spin quantum number of the second electron to produce the total spin quantum number S of the electron or the atom. Then capital L will combine with capital S due to LS coupling, and then you see that the total angular momentum quantum number J of the electron or the atom will be constructed. So this is the picture corresponding to the LS diagram. Similarly, now I am going to give you the diagram of the JJ coupling. Again, you see that I should produce this diagram with orbital magnetic moment and the spin magnetic moment. But you see that for simplicity, I am going to draw this diagram using the quantum numbers. So you see that the red one indicates that it is the same electron, and the sky one indicates that it is the same electron but different from the first electron. So this red is for the first electron with orbital quantum number L1 and with the spin quantum number S1. These SL1 and S1 will combine together to give you the total quantum number J1. This is the JJ coupling. So L1 and S1 of the same electron will combine together to give you J1. Similarly, L2 and S2 of the same electron, which is the second electron, will combine to give you J2. So J1 and J2, that is the J1 corresponding to first electron and J2 corresponding to second electron, now they will combine together to give you the total value of J. So this total value of J produced by the LS coupling will be identical to those of the LS coupling. So you see that I have given the schematic representation of both LS and JJ coupling. I hope that through this picture, it will be easy to understand that what happens in the JJ coupling. Individual orbital and the spin angular momentum of the individual electrons combine together to produce individual total angular momenta J1, which then combines with the other with the total angular momentum of the other electrons to produce the total value of J. So this is called a JJ coupling. If there are n electrons, you see that I have discussed this picture for the JJ coupling only for the 2 electrons. So if there are n electrons in an atom acting as the valence electrons, then you see that L1 plus S1, that is the orbital angular momentum and the spin angular momentum shown in vectorial form, will combine to give you J1, which is the total angular momentum due to electron 1. Similarly, L2 plus L2 will combine together to give you J2, that is the total angular momentum of the electron 2. Similar and so on and so forth. Then finally, the Ln and the Sn, that is the orbital nth orbit, that is the orbital angular momentum due to the n electron, and the spin magnetic and the spin angular momentum due to the nth electron will combine to give you the Jn, which is the total angular momentum of the nth electron. And then of course J1, J2 and Jn will combine together to give you the total value of capital J of the of all the electrons or the atom. So you see that Js for a different value S combine vectorially to give you the total angular momentum J of the atom shown in equation number 13. That is capital J is equal to the vectorial summation of the individual values of Ji due to individual electrons. Now you see that I have shown the magnitude of this capital J shown on the left hand side in equation number 13. I have shown its magnitude on the left hand side of equation number 14. So this J mod is actually the magnitude of this total angular momentum J of the atom. And it's given on the right hand side by the square root of J into J plus 1. Here this J on the right hand side are the quantum numbers, where J on the left hand side is the angular momentum, and multiplied by h bar on the left hand side, which is outside the square root sign. And so you see that this okay, and then you see that here in the JJ coupling, the total value of capital L, that is the total value of the angular momentum, is not defined. So the resulting orbital angular momentum is not defined in case of JJ coupling. So no term symbols, that is S symbol, P symbol, D symbol, and so on, these symbols will not be used because these symbols are associated with the value of capital L, that is the value of the orbital angular momentum or the orbital quantum number. Since we have no orbital angular momentum and no orbital quantum numbers, so there is no question of the term symbols S, P, D, and so on. The new term notation will be J1, J2, and outside the parentheses we shall specify as a subscript the value of the total value of J obtained by combining J1 and J2 for the individual electron. So we shall write these states for the individual electrons. The number of possible states for capital J values are the same as in LS coupling. So the value of J will be the same in the number. So the same value, so number of terms will not change as in case of LS and the JJ coupling. Same number of terms will appear. So here I am going to give you the LS coupling, the JJ coupling. These are the extreme cases. LS coupling on the left hand side, JJ coupling on the right hand side. LS coupling is applicable to lighter atoms. JJ coupling is applicable to heavier atoms. Of course, there is some intermediate range also, in which neither the LS coupling nor the JJ coupling is applicable. So here are different types of applicables, couplings will be applicable. If I find appropriate time, I shall be discussing those intermediate couplings also. And you know that, okay, for the intermediate coupling, delta S is equal to 0 is not strictly valid. Because you know that delta S is equal to 0 is strictly valid for the LS coupling. But here I have shown that for the intermediate coupling, for those atoms which are neither lighter nor much heavier, then of course the intermediate coupling will be applicable to such atoms. And for those atoms, delta S is equal to 0 is not strictly valid. That is, the transitions between different multiplicity states will be possible. In higher pressure mercury lamp, for example, lambda is equal to 253.7 nanometer is an intermediate combination line between the singlet and triplet states. So you see that here you can see that the transition from the triplet and singlet is possible for this high pressure mercury lamp, which gives you 253.7 nanometer wavelength. And of course, here delta S is equal to 0 is not strictly applicable. That's why the triplet to singlet transition will be possible. And this may fall in the intermediate coupling range. So the selection rule for the optical transition for the JJ coupling is delta J is equal to 0 plus minus 1. And from J is equal to 0 to J is equal to 0 transition is forbidden. That is, if both states have the value of J is equal to 0, then the transition between them it will not be possible. But however, if one state has a value of J equal to 3 by 2, the other value has J is equal to 3 by 2, then the difference between them will be equal to 0, and then of course such a transition will be possible. Now you see that I want to emphasize that if we move from LS to JJ coupling, what will happen? So the transition from the LS to JJ coupling in the series, for example, from the carbon to the silicon, carbon may be categorized in the lighter atom, and then we are moving towards a heavier atom, then from the carbon to the silicon, then silicon to the germanium, then from the germanium to the tin, then from the tin to the lead, and the lead is the heaviest among these. So this will be shown, their spectra will be shown in the next page. The ground state configuration along with Z values are shown for these atoms. That is, for the carbon atom, we have the ground state as 2p3s with capital Z is equal to 6. And for the silicon, I have the ground state as 3p and 4s with the value of capital Z is equal to 14. And then for the germanium, I have the ground state as 4p and 5s with Z is equal to 32. And then for the tin, I have the ground state as 5p and 6s and the Z is equal to 50. And then for the lead, I have the ground state configuration as 6p and 7s with the Z is equal to 82. And you will note that all these, for all these atoms, the ground state has the same electrons, that is the p electron and the s electron. Though the principal quantum numbers are different, but the orbitals are the same. That is the p electron and the s electron is all present in all these ground states of these atoms. So analyzing the one of these atoms will give you the same splitting, will give you the same splitting, or will give you the same JJ levels. will give you the same levels obtained from the JJ coupling, because they will depend upon the value of P, or from the value of P and S, which is the same for all these ground states. So JJ coupling for the states, so NP and N prime S, where for the carbon atom N prime is equal to N plus 1. For the other atoms, you can see that this is also applicable for the other atoms, but this N will change. For example, for the carbon atom, this N is equal to 2. For the silicon atom, this small n is equal to 3. For the germanium atom, this n is equal to 4, and so on. So you see that I have selected p electron and the s electron, for which forms the general ground state for these atoms. So L1 is equal to 1, S1 is equal to half. Similarly, for the second s electron, I have L2 is equal to 0 and S2 is equal to half. So L1 and S1 can be combined to produce J1. So J1 is equal to mod of L1 plus S plus minus S1 will give you mod of 1 plus half, will give you two values, 3 half and 1 half. Similarly, J2 obtained for the S electron will combine mod of L2 plus minus S2, that is the mod of 0 plus minus half, which will give you 1 half. Now you see that I shall be combining J values. So J1 and J2 will now be combined to produce the resultant J of the atom. And in that case, I am showing these values over here. So capital J is equal to mod of J1 plus J2, and J1 has been represented by the terms in the parenthesis. The first value of J is red, is shown in red, which is 3 half, and the second value is shown in black, whereas the value of J2 has been shown in blue, so that we can make a discrimination between them. So you see that when you combine these two in the value of a mod, you will get the first term due to combining with 3 half. When this 3 half shown in red is combined with the blue term of 1 half, you will produce two red terms shown in parentheses, shown in curly brackets as 2 and 1. So this is the total values of a capital J. So similarly, when 1 half and 1 half shown in black and 1 half shown in blue will combine together, you will produce two black terms shown in curly bracket as 1, 0. These are the four values of capital J. So you see that I have represented these four values with their corresponding terms. For example, with the term 3 half shown in red and the 1 half in blue, these two were combined to produce total value of capital J to 1. So I have written to 1 with that one. Similarly, 1 half in black and 1 half in blue have been were combined to produce the total value of quantum number J as 1, 0, which I have written as the subscript with the corresponding terms. So these are the four JJ terms. You know that if I had applied the for example the ls configuration to these terms, I shall obtain the terms which will have the lowest value of j equal to 1, then the j value equal to 2, then the j value equal to 1 and 0. So you see that then these values of j will be arranged according to the ls coupling. So in the LS coupling, the value of J is equal to 0 will be the lowest in energy, then J is equal to 1, then J is equal to 2 will be the higher in energy, then J is equal to 1 will again be higher in energy. This is the distribution of energy terms in the LS contribution. But you know that I have to arrange the JJ terms which are obtained over here and which I have written over here. So I have arranged these terms in the same pattern. The value of capital J is arranged for the LS coupling. So these are the J terms, and these are the arrangement of J's terms in the spectra. In the spectra of what? In the spectra of these atoms. That is the carbon atom, the silicon atom, the germanium atom, the tin atom, the lead atom. So if you find out the coupling, LS coupling or the JJ coupling, you will get always the four terms like this. And this is what I have shown their couplings in terms of JJ couplings, assuming that I am talking about heavy terms, heavy atoms. So you see that now I am going to give you the distribution when we move from the carbon atom, that is the lighter atom, to the lead atom, which is the heavier atom. So you see that I have written, I have carbon atom, silicon atom, germanium atom, tin atom, and lead atom, and I have written down here ground state configurations, which is 2p3s, 3p4s, 4p5s, 6p6s, and 5p6s, and 6p and 7s. And for the carbon, I have shown the LS coupling. And for the LS coupling terms are the highest energy term is 1p1, and the lowest energy terms are 3p0, 3p0, 3p1, and 3p2. So these are the four energy terms due to LS coupling. Then you see that I have in some types of intermediate coupling, and you can see that how the levels will split in the intermediate couplings for the silicon. Then for the germanium, you can see there is a switch over of energies for the germanium atoms, that the levels have been switched over here. Then of course I have moved to the tin atoms, the levels are further apart. And then for the lead atoms, the levels are the highest in separation. And you can see that their energies are, so this is the JJ coupling for the highest energy term, which is the lead term, with configuration 3p and 7s. So these are the four terms that I have shown for the lead atom. And you can see that as we move from the lighter atom to the heavier atom, you see that you can see that the separation between the levels is increased, and their measurement becomes much easier for the heavier atom. But you know that there will be a problem for the heavier atoms, that if there are some other states, those states can mingle up with the energy terms of the lower states. For example, if there is another state higher to the ground states of these atoms, their energy terms will also mix up with the energy terms of the ground states. So then, of course, it becomes much difficult to find in the spectrum to analyze which states corresponds to which state. That is, the state either corresponds to ground states, or to the first excited state, or to the second excited states. It becomes much difficult in the spectra, because the separation for the heavier atoms becomes much larger. Now you see that for the carbon atom, I have shown some wavelengths. And you know that the levels for the carbon atoms in the LS coupling have been shown as 1p1, 3p0, 3p1, and 3p2. These are the four levels. And I have shown some transitions between them, which are important transitions for the carbon atom using LS coupling, as 3p0 to 3p1. This transition will give you a wave number in 20 centimeter inverse. Then from 3p1 to 3p2 will give you a wave number as 40 centimeter inverse. Then from 1p1 to 3p2, the wave number is 1589 centimeter inverse. So I have not shown the transitions from the other, because these are not relevant over here. The purpose was just to indicate the LS coupling, and to compare the LS coupling with the JJ coupling, and also what happens in the intermediate region to these levels. And we have noticed that the separation between the individual intermediate levels will increase, and of course sometimes the levels are swapped, that is, their positions are interchanged. Now, the magnetic moments of many electron atoms. For many electron systems, the total angular momentum of an electron is given by. So this is the magnitude of the total angular momentum, capital G, which is equal to the square root of J into J plus 1, and outside that one we have H bar. This J within the square root sign are actually the total quantum numbers, and this J with the vector sign on the left hand side is actually the total angular momentum of the atom. And you know that this capital J is given as mod of L plus minus S using the LS coupling, and this capital J is given as the summation of this vectorial form. I should write vectorial vectors on this J and also on this small j on both sides. So vector J, that is the total angular momentum of the atom, will be equal to the vectorial sum of the individual individual angular momentum of the electrons, individual total angular momentum of the electrons, which is the case for the JJ coupling. You know that, okay, I have shown total J for the LS coupling, I have shown total J for the JJ coupling. For both of these coupling, the mu L and the mu S are combined to give you mu J, where mu L is the orbital magnetic moment of the atom, mu S is the spin magnetic moment of the atom, and mu J is the total magnetic moment of the atom. Where mu S, you know that this statement can readily be written for the LS coupling, because in the LS coupling, the spin, the orbital quantities exist there. But in JJ coupling, the orbital quantities do not exist. So mu S is equal to the spin magnetic moment anti-parallel to capital S. Mu L, which is the orbital magnetic moment, is anti-parallel to the to the value of capital L, where capital S and capital S are the spin angular momentum, total spin angular momentum, and capital L is the total orbital angular momentum of the atom, and mu S is the total spin magnetic moment of the atom, and mu L is the total orbital magnetic moment of the atom. GL factor, which is the Lande GL factor. GL factor was different from the GS factor, because for the spin we have the GS factor, for the orbital quantities we have the GL factors, and we have discussed GL and GS in one of the previous lectures in much greater detail. So due to which GL factor was different from the GS factor, due to which mu J did not coincide with J. And in one of the previous lectures, we have also seen that the directions of mu J is not exactly anti-parallel to the direction of J. So mu J was slightly different from the direction of the anti-parallel direction of J. Instead, mu J recesses around the direction of J. Only the projection of mu J in the direction of J was observable. Okay, and this is what I have discussed in one of the previous lectures, where I have discussed the precessional motion of these quantities in the presence of the magnetic field. So you should consult these in the in the lectures on the topic of atoms in magnetic fields or atoms in electric fields also. Now you see that from lecture number 13, from slide number 13, equation number 38, and from slide number 13, equation number 39, we have these following quantities which I have reproduced as equation number 15 and 16 respectively. So this is the jth projection of mu J. This is the magnitude of the jth projection of mu J, which is given as 3 into j plus 1 plus s into s plus 1 minus l into l plus 1 divided by 2 times the square root of j into j plus 1, and this whole term is multiplied by mu b, where mu b is the Bohr magneton. And then another same relationship but in different form is given in equation number 16, where the magnitude of the jth component of the mu j is equal to gj into the square root of j into j plus 1. Outside that one, we have a mu b. So you see that the left hand side of both equation number 15 and 16 are equal. So I can compare their right hand side and can solve for the value of gj. So you see that the value of gj as shown in equation number 17 is given. So gj is equal to 1 plus j into j plus 1 plus s into s plus 1 minus l into l plus 1 divided by the denominator, which contains 2 times of j into j plus 1. And you know that this j's, This J value, S value, and L value in equation number 17 are respectively the total quantum number, the total spin quantum number, the total angular quantum number of the atoms respectively. And Gj is actually the Lambda G factor for this system, which you can use for the JJ coupling also. In a chosen direction, which is the Z direction, the magnetic quantum number mg is quantized. This is also what we have seen, and their quantized value is given by, that is their z value. So the z component of the jj and mu j, and that is the z component of j of mu j, or you can say that is the projection of jth component of mu j in the z direction, which we write as mu j of j comma z is equal to minus mj times gj times mu d. So these are the values of the z component, and you know that these are the values which can be measured experimentally, because these values stays the constant. The other two quantities which has the x component and the y component, those two values will be averaged out to zero, and those quantities due to the precessional motion will not be measurable under the application of the magnetic field. And you know that the magnetic field will be the same as this z direction, and mj, which is the magnetic quantum number of the atom, will have the values j, j minus 1, j minus 2, and so on up to minus j. So mj takes integral or half integral values depending on the values of j being an integer or being half integer, and you need to produce all the values between plus j and minus j. The intermediate values with the difference of integer values will also be reproduced. The measurements of mj of atomic states are obtained from the splittings of the spectral lines. So when you apply the magnetic field, these spectral lines further split due to the lifting of orbital degeneracy of the mj levels. Then measuring the splitting between those levels in the presence of the magnetic field, the splitting of spectral lines are determined, and from that one the value of mj is determined. LS coupling breaks down in sufficiently strong magnetic fields, and these could be the internal magnetic fields of the atoms also. And in very strong magnetic field, even the JJ coupling breaks down due to the heavier atoms have internally strong magnetic fields, and due to that one their coupling will be different. That's why the JJ coupling will also be broken down in case of much heavier atoms, and of course some other coupling techniques will then be applicable. And even if you have a moderate atom, and if you apply stronger magnetic field, even then you can treat those atoms in the category of JJ coupling. But if your magnetic field is much stronger, even then the JJ coupling for such atoms is also broken down. The case of multiple excitations, especially for the heavier atoms, is much difficult to analyze, because for the multiple excitations, study of heavy atoms in which states of several electrons are changed with multi-photon excitation with strong mutual interaction between electrons presents a complex picture. So you see that the atom is heavier, and even we are using the multi-photon excitation. Due to that one, there will be a complex values, there will be complex number of spectra, and then of course there will be complex interactions between the electrons, and then of course due to complex interaction the spectra is complex, and such a complex spectra is difficult to analyze. A light contact can simultaneously removes an electron while exciting other one to be excited, to be in the excited state. That's why it will be different. Sometimes the excitation and de-excitation occurs simultaneously, and the spectra becomes slightly complex. This makes analysis of the heavy atom spectra much more difficult. So you see that now this is the end of the series of many electron atoms. I have delivered 4 lectures labeled as 15A, 15B, 15C, and 15D, and I have tried my best to explain the many electron spectra, and especially the emphasis was on LS coupling and the JJ coupling. And I have explained the LS coupling in much greater detail, and I have given some detail so that you can understand the JJ coupling. There are some intermediate couplings which I have not discussed yet, but if I could have some time and opportunities, I shall be discussing about those intermediate couplings also. So now this is the end of the series of lectures on many electron atoms, and also this is the end of today's lecture.